0. I'll try to. Okay, set. Ooh, yes. Right, so we're changing the subject slightly, although we will go back to the page ranking ideas a bit in maybe a couple of weeks' time, maybe a bit longer. What we need to do in order to, well, there are two main reasons for this switch. The first one is because you, as studying big data, as a computer scientists and mathematicians studying big data, you need to know something about probability. And because we're trying to bring everybody here up to speed, to the same level, that you can start in the next semester learning more about applying these ideas, then the idea of this course is to bring everybody up to speed in probability. And we'll just touch upon statistics in that course, but mainly it's just the foundations of probability and then the ideas, the probability distributions. So there will be three main blocks. The first one will be just an introduction, and that's something we're talking about largely today. Then there will be a concept of a probability, what the probability is, how we operate the probability, conditional probabilities, Bayes' theorem. There will be these different ideas. And then the third block is about some very selected probability distributions. So we'll just give a couple of examples of probability distributions. I will try in between to squeeze a lecture on extending the idea on a bit on Markov chains and and the stochastic processes, and link it to the page ranking algorithm, just to show you how these two things actually dovetail very, very nicely. So the linear algebra and probability theory, although they might seem like something completely the poles apart, they're actually very, very close together. And I think as a sort of, if you want to work on big data, you need to know about Markov chains and stochastic processes. Okay, it will be just a very, very short introduction to this. So what we're talking about today, it might sound very mundane and might sound very simple. And I said the idea of this is to bring everybody up to speed on a number of ideas. So today's lecture, again, you might find very simple if you've done probability in the past. Okay, so the idea, what we're really talking about is the introduction to probability. Once we get to probability, please remember to shut me up, because I might talk about probability and the interpretation of probability for too long. So just make sure that somebody waves their hand and says, please do stop talking about that, start talking about something that we really need to know. Okay? Because it's one of my hobby horses. Anyway, before we do this, we need to do a bit about set theory. If you're following the book, what we're doing here in this section is we're looking at chapter 35 in the book, and it's all about set theory and Venn diagrams. But it's really, set theory in itself is a very interesting subject, but also there are it's linked to the idea of a logic, and particularly computer logic. So things like and, or, XOR, and so on, that's actually, you will see this in what I'm going to talk about. There are very, very strong links between those things. Okay, what is a set? In set theory, formally speaking in mathematics, a set is something that's not defined. It's just introduced as an axiom, in a sense. But essentially the idea here is a set is a collection of things. And in a very general sense, it can be a collection of anything. In what we will be really working on will be sets of numbers and will be sets of elementary events. And elementary, those are the two examples. I'll talk about events a bit later, but essentially if you want to think about an example of a set for this part of the lecture, then think about numbers. I will be denoting sets by capital letters, S, A, X, B, C, and so on. Hopefully you will not mix those with matrices. Those are very, very different beasts. I will also use one letter. So Jordan and Smith uses a letter U to denote a universal set, and it uses the letter S to denote the sample space. I will be using a Greek letter omega. So hopefully you will sort of be able to correct Jordan and Smith and sort of write on. Sorry?
Instead of the U?
I will be using this. I'll come back to this in a moment. I'm just talking about notation here. Okay. So this is not a very nice, nicely written Greek letter omega. Okay, capital letter. Right. If I want to list the elements in a set, I will be using curly brackets. So for example, a set could be 0, 1, 2 is a set of 3 elements. So 0, 1, and 2 are elements in this set. This is if I can list all the elements in a set. In many cases, I want to give a definition rather than, so I want to give a rule rather than a list. In that case, I will be writing, I very often will write that this is X, and then vertical line means it's all X that satisfy a rule. Okay? So what comes later will be a rule. So for example, if I say that A X such that let me just think of a good example. So X, I'll come back to this notation in a second. This will mean it's a real number and it's between 0 and 1. Okay. So for this notation, as I said, I'll come back to this in a second, but this will mean X is a real number and it's anything between 0 and 1, including 0 and 1. Okay. So it's giving a definition by rule. Another important concept is a concept of belonging. So if I have a set A, then a certain element belongs to A. And that means that this element is in A. Again, what it means, element belongs to a set, in sort of formal mathematics, is something much more complicated. As is the definition of a set, but let's just stick to just the simple things. So for example, if A is 0, 1, 2, then 0 belongs to A, but 3 does not belong to A. Okay. If A is a set of all real numbers, such that X is between 0 and 1. Now, you might be already familiar with that. This is an interval on a real axis between 0 and 1, including 0 and 1, and then 3 does not belong to A. Okay, let's call it B, so that we don't get confused. So 3 does not belong to B. The rule, like this, allows me to avoid listing all the elements. And in fact, if I want to list all the elements in this set, I can do this easily. I mean, it's just 0, 1, and 2. If I wanted to list elements in that set, well, I will be spending the next few hours, or quite long actually, trying to list all these elements. Okay? Because there are infinitely many elements in that set. So some sets are finite, and that's, for example, a set 0, 1, 2 is finite. Some sets are infinite, but can be counted. For example, a set that x is an integer, so I'll just write it this way, 0, 1, 2, 3, and so on. Okay. I mean, obviously, you need a bit of imagination what these three dots here mean, but it just means 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. There are some sets that are infinite, but uncountable. And for example, an interval 0, 1 is uncountable. So I cannot count, with fingers the numbers that are over that set. And there are, of course, even more complicated beasts, because there are actually sets that have more things in it than this set. Well, no, this is a little too complicated.
It doesn't consist of two elements, 0 and 1.
Sorry?
It doesn't consist of two elements.
No, it's not two elements. But this is, do you know this notation? Does everybody know this notation? This is interval. So it's all the real numbers between 0 and 1. All right. If I wanted to list the elements, I would be using the curly brackets. Yeah. Square brackets means all the real numbers between 0 and 1. If I wanted to use ordered, and I might do this, then I would use round brackets. But I'll talk about ordered later. Okay, are we all right so far? It's just a very, very brief introduction to sets and set theory. Some special sets. And I've already included some of them in a notation up there. The R is real numbers. Again, I'm not defining what a real number is, because we'll be spending quite a long time if we wanted to do this. But you get the feel, you know what a real number is. Most of you. Complex numbers, so it's all the numbers of a type x plus iy, where x and y are real. Then integers, so this is numbers of a type minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, and so on. Okay. So those are integers. N means natural numbers, and there are actually two conventions. There are two ways. I think Jordan and Smith uses N to denote 0, 1, 2, and so on. Some of my more pure mathematician colleagues would really object to that. For them, N starts at 1. This is what Jordan and Smith uses. N plus is 1, 2, and so on. Okay. It doesn't matter. I mean, don't really worry about that. I mean, it's just a notation.
Sorry,
here.
is the Z?
Z. It's integers.
Okay.
Q is rational numbers. So it's numbers of a type. So it's x equals p over q, or actually we could write this as p divided by q, such that p and q are integers. Okay. Sorry, I probably need to write it on the next page. So I'll just write it here. Q is p over q, such that p and q are both integers, and q is not equal to 0. Okay. So those are rational numbers. equality of sets. Again, it's a it's a complicated issue, particularly if we're talking about infinite sets or uncountable sets. What does it mean that two sets are equal? Essentially, for the purpose of here, I would say that A equals B if all elements are in A are in B, and all elements in B are in A. Okay. So that there are the same elements. So two sets are equal if they have the same elements. As I said, this is a very open problem if you go into infinite sets. Right. As I said, I will be talking about a universal set. And Jordan and Smith uses U, and I will use omega. It's essentially a set that contains all the numbers or all the elements that I'm interested in. So this could, for example, be all real numbers or all integers. And very often I will be limiting that even more. So I'm saying I'm just interested in a certain set of numbers. Okay, so that's a universal set. Then a big, so we know what the sets are. Now the real fun and the real power becomes when we can combine sets. And actually, before we go into combination set, I mentioned equality. I also mentioned subsets here. I'm jumping slightly ahead here. So I will say that A is a subset of B if every element in A is also in B. So note there is this, so it's like a U, but on the side. Or you can think it's like a belonging, but without this little horizontal bit in the middle. But it's got this equal sign here as well. That means that A can contain all elements, so all elements A are in B, but we don't know about the rest. Okay. There could be elements in B that are not in A, or not. A stricter definition is a strict subset or proper subset. So this is a proper subset. And that's if every element in A is in B, but not every element in B is in A. Okay. So that these three things, these three definitions, equality, a sort of weak inequality, and the proper subset are sort of exhaust all possibilities. Actually, there's a fourth possibility. I'll come back to this.
A subset can be equality?
A subset can also be, I mean, this is a subset. A is also a subset if it's, well, if we don't know whether it's equal. It can be equal.
Okay.
Because then it's a bit of a semantic. I mean, it's more like I will be, in some assumptions, for example, I will be assuming that, and I stress that this will then work both in both cases. So both if A is a proper subset of B, but will also work if A is equal to B. Okay? Whereas with this, I want to stress that A is a proper subset of B, okay? That they're not equal. Right, combinations of sets. So if A and B are sets, and I will here, I will just limit myself to the case where they're both subsets of omega, although that doesn't need to be the case, but let's assume they're all subsets of omega. Then a union of two sets, so union of AB, is denoted with sort of like a small u, and that is a set of all the elements such that X is in A or X is in B. And note here the word or. So, for example, if I'm stressing this link here because as computer scientists or budding computer scientists, you might want to think of these things in terms of computer logic. So things like and or. There is a very strong connection here of those two things. In fact, when I was a student, in the first year, we had a module where the first half of the module was about logic. So about statements, whether two statements are true or false, and how you combine statements. And then we build upon that with sets. This is a logic statement. So X belongs to A or not. It's either false or true. This is also false and true. So essentially what I'm doing here is I'm combining two statements. Okay? And that links these two statements to the set algebra. And I'm not doing this here, I'm just jumping straight into sets, but you might find it sort of more useful to think in terms of the computer logic here. Intersection. I'm not sure I like this part of the module actually when I was a student, but I found it very useful afterwards. So, intersection of A and B. What do you think? It's a linking word? And. Very good. Thank you. That was... Okay. So that's the idea. So it's an intersection. Okay? It's two statements. X must be in A. X is in A is true. And X in B is true. But both of them must be true. Complement of A. This is an operation that acts on one set, but actually you need to specify that the universal set. Okay? We can only talk about complement of a set in relation to another set. So, and then there's different notation, and I might actually mix the notations here, so I apologize, but in advance. Sometimes it's denoted as a bar on top of the symbol A. Sometimes it's denoted with an A with a little C for complement. Sometimes it's denoted with the little sign there. And there are many other ways that people denote the complement. Okay, I tend to use either the first or the second one, and I might, as I said, I might use both in calculations. So that's a set of X such that X is in omega, but is not in A. Right, so we've encountered one special set, omega. There's another special set, which is called empty set. And that's denoted by a sort of a little circle with slash. So that's, I think I'm not sure whether it is a Greek letter phi. I think it might be either a Greek letter, I mean, there is a Greek letter phi that's similar to this. I'm not sure where that comes from. So anyway, it's a circle with a slash through it. Again, this is something that it's very difficult to define. In fact, in the axiomatic set theory, we actually start with an empty set and then build sets on the basis of an empty set. Okay, so you start with an empty set, and then a set with a one element is a set that contains an empty set. And then you can have set with two elements, which is a set that contains an empty set plus an empty set, and so on. So that's how you build the set theory. But no, don't worry about that. It's sort of me going off the beaten track here. So empty set for you should be a set that doesn't have any elements. Okay, let's have a look at some examples. Now, you might be wondering, before I go to examples, you might be wondering why we're bothering with that. And the answer is that a proper way to introduce the concept of probability is to go via sets. So what we will be looking at, the basic thing, if I can get to it today, I'll try to get to it today. There will be the basic concept in a probability theory is a concept of an event. And it was actually sort of the Russian mathematicians in the beginning and the middle of 20th century that actually made this connection and built a rigorous probability theory based on set theory. So this is one reason, I mean, that's the reason why we like doing this, because it's a rigorous way. The other one is that in a probability theory, in a probability in applications, we will be combining events. So we'll be talking, for example, about a case, what's the probability that there is a nice weather today and a nice weather tomorrow?
It's Scotland.
Sorry?
It's Scotland.
We always have nice weather here. It's always beautiful weather. It might not be very sunny. So we would need to learn to combine these things. And that's the way we combine. We combine by using these words and, or, not in, and so on. And that will allow us to manipulate, to learn about probabilities. And that's why we're bothering to do this. Okay? Plus, it's something that you as computer scientists should at least have some, also sort of data scientists should a bit know about. Okay, some examples. Suppose that A is the set of X such that X is a real number and X is between 0 and 2. These are examples, by the way. You can look them up in Jordan and Smith. So I'm using primarily examples from Jordan and Smith. Okay, so really, if I want to represent it on a line, on a real line, so if this is a real line, then if this is 0, this is 2, so this is this interval. Okay, so it's anything between 0 and 2. And set B is a set of X such that X is in R and is between 0 and 3. So if I want to represent this on a line, it will be again from 0, but now extending to 3. So that allows me to, I'll redraw this below because I haven't allowed enough space there. So that's a real axis. Then one set is between 0 and 2. And the other set is between 0 and 3. Is that the wind howling outside? Yes. Right, so let's look at how those two sets combine. So a union of the two sets is X such that it belongs to either A or B. So it's everything from 0 to 3. Okay? Because if it's between 0 and 2, it actually belongs to both. And if it's beyond 2 and 3, it belongs to B. And that's okay. It's okay if it just belongs to one of them. So that's a set of real numbers such that X and 0 between X and X between 0 and 3. An intersection of B is a set of X and, now let's think what the intersection is. The intersection needs to belong to both. So what's the intersection? 0 to 2. Okay, so everything here is there, so 0, X to 2. Okay. By the way, the complement of A, let's think of a complement of A. Now the complement of A is everything that does not belong to A, and we need to define what the universal set is here, but let's say this universal set is R. Okay, that's suggested by this bit here. So that means that it's everything here and everything here. Okay. So that means it's X such that X is in R and X is smaller than 0 or X is bigger than 2.
Can you see X not belong in R?
Sorry, say it again?
Can you see X not belong in A, in R?
You could, yes, of course, yes. But I wanted to be more constructive here, so say what they are. In fact, we've already used implicitly a lot of rules that I'm going to talk about in a moment. That are called De Morgan rules. So, for example, what you just mentioned just a second ago, I could have rephrased this by saying not like this. Yeah. I could have said this, and actually the way to write this would be not, because what does it mean that X is between 0 and 2? It means that X is bigger or equal 0 and X is smaller than equal 2. Okay. So I just want to signal here the fact that a combination of not and and gives us or. Remember that? We'll need it in a few minutes' time. But the reason, these are the so-called De Morgan rules. Again, they come in logic first, but they can be used, extended to sets. But they sort of capture the way we think. So there isn't anything outlandish in here. It's just the way to trying to capture the ideas, the way we think, we form the concepts. Sorry. Okay. Do I want to do another example? I think you're okay with that. There are some more examples in Jordan and Smith. Right, algebra of sets. This isn't linear algebra. Just make sure you don't confuse those two things. Algebra of sets essentially means rules that govern the combinations of. So what the properties are of these two operations. So we included 3 operations, in fact. We included the complement, union, and intersection. And essentially what we want to do is we want now to show what are the properties of them? And again, in a proper set theory, we will probably start there, here. So we would say, let's define these three operations, and those are the principles that are governed by those. Right. There's a number of different properties. So A union A is A intersection A is A. So if I have an element that belongs to A and belongs to A, it means it belongs to A. Okay. If I have an element that belongs to A and belongs to A, did I say and before, or did I use or? I should have used or here, I should use and here. But, I mean, it's trivial. Right, a bit more. A union B is the same as B union A. A intersection B is the same as B intersection A. And that has a name. And you probably remember this means that both union and intersection are commutative. I can commute those.
Excuse me.
Yes?
Can you explain the commutative once again?
Can I explain what?
Commutative.
Commutative. It means that the order doesn't matter. The second one is A union B union C is A union B union C. A intersection B intersection C is A intersection B intersection C, and that means I can group them. I can group things, I can group operations as I like. And that's the name for this is associative. And the next property is that A intersection B union C is the same as A intersection B union A intersection C. You see, we're sort of making it more and more complicated. A union B intersection C is A union B intersection A union C. Sorry? A union B, yes, A union C, sorry. I was probably saying that, but writing wrongly. Thank you for doing this. And the name for this is distributive. If you go back to a few lectures, when I talked to you about additions and multiplication of matrices, I've used exactly the same words. I don't want to push this analogy too far, but it is actually, there are sort of similarities there. This is sort of where mathematics comes in, where people start thinking, okay, I can use matrices, I can use sets, the structure is the same. But let's don't push that too far, okay? It's just maybe you find it easier to remember those rules if instead of addition and multiplication, instead of union and intersection, you will think about addition and multiplication. And it's just, it's mainly for remembering things. There are a few more. A union empty set is A. Intersection empty set is empty. A union universal set is universal set. A intersection universal set is A. So, essentially, if I have a set A, and I add to it an empty set, I still get an A. Intersection, if I have A, so something that belongs to A and belongs to an empty set, nothing belongs to an empty set. So the answer must be nothing here. If I add elements in A to the universal set, I'm only doubling these elements, and we don't double elements here. So that means I'm just getting a universal set. And then the universal set, A is essentially a subset of A. This is what it means. Of omega. And then the final one, the final rule is that A union not A, or a complement of A, is omega. So if I have something that is in A, and something that's not in A, if I add these things, I get the universal set. And a intersection not A is empty. Again, this is clear. And also A complement is A. And that's essentially a rule of a double negation. So if I have something that doesn't belong, that's not true that it doesn't belong to A, it means it does belong to A. And the final one is the last operation on sets that I want to introduce, which is the difference of sets. And A difference B, you could think of this as minus, but it's not. It's usually not as a horizontal line. It's usually as a slanted line. A minus B is a set of all elements X such that they belong to A and they not belong to B. Okay. So we've got lots of rules. All of these rules are intuitively clear. The problems in maths become, I mean, this is well stated for two sets. You can actually generalize this to more sets. We try to generalize this to a countable, infinite number of sets, and things become a bit more complicated. But again, let's not go into this. So we will just be talking about finding that. Yes?
Could you repeat what you said about the A in the parenthesis with 2 lines above it?
This one?
Yeah.
So, okay, let's just do good. Okay. In fact, most of this will come as theorems, and they will come, and they will be a result. We'll use in the theorems the elements of logic. So, but here, let's just look at that. So A naught, let's just do it in black. So A naught is a set of X such that X is in omega, but it's not in A. Yeah? Then A, double that, it's a set of X such that X does not belong to A dash. Yeah. So this is a set of X such that it's not true that X belongs to A dash. And that's the same X such that it's not true that X belongs to A. Okay? Because X belongs to the complement of A if it doesn't belong to A. Okay? So I get not, and there is a logic, again, another property in logic that says a double negation cancel out. So not means that X belongs to A. And that, of course, is by definition A. Okay? You can actually, all of that can be proven using logic, or actually, you assume things in logic, so things like, and if I have two statements, and they're connected by and, if I add another statement that's connected by and I can prove either this or that. This all comes from the logic. Okay. However, once we've got this algebra here of sets, there is lots of things we can prove. There are sort of many, many more properties of these operations, but we can prove them using the ones in blue here. And this is what we're going to do in a few minutes. Before we have a short break, I just want to introduce one more concept, and that's called Venn diagrams. It's V-E-N-N. Somebody should check who Venn was. I forgot. I used to know, but I forgot who Venn was. Anyway, the whole idea is how can we visualize this? And I've already done that with the real axis. And essentially, a Venn diagram is a generalization of that. And the concept here is that, and it's usually done in this way, that a box like this denotes the universal set. And within this box, we draw circles or more complicated shapes sometimes to represent sets. So a typical drawing might look this way. Okay. So, and that's a Venn diagram. And we also use shading. We use shading so to denote some parts of sets. And you can already see that if this is A, then everything that's outside is a complement of A. And from that, you already see that A complement union A is omega. Because everything outside plus everything inside gives me the whole thing. So that's a way to illustrate. We use these things to prove, because it's not a proof as such, it's an illustration. But I'm very happy if you were to prove things. If I ask you in an exam, or if I ask you in an assignment or in a tutorial to prove something, and you use the Venn diagram, I will accept it. If you don't want to use a Venn diagram, you want to use the logical statements, feel free to do that as well. Okay? So we will accept Venn diagram as a proof, realizing it's not a proof, it's an illustration. Okay? 10 minutes break. Thank you. So, excuse me. Hello. Thank you. Okay, so that's so Venn diagrams. The idea here is that we would use these Venn diagrams to prove things, to illustrate some concepts. So let's have a look at some. So this will be our omega again. And then we can have set A and set B. And we usually do this in a sort of most generic way. Okay? So, I mean, obviously A and B might not have any intersection, but we just look at this. So we can just look at different elements. So for example, what's inside here, this is A intersection B. In fact, what's inside here, well, let's just think for a moment what's here
B minus A minus
is B minus A. It's B minus A. Sorry, what did you say? A minus B. Okay. And this one here, well, this is exactly what we just were talking about just a moment ago. This is B minus A. Okay. What about the whole thing? Very good. So that's A union B. So in this way, we've just proven a very nice theorem that A union B is A minus B union A B minus A union A and intersection B.
Sorry, what's the notation you're using between the A and B, the minus? Is that slash?
This is slash.
Yeah.
Let's just...
backslash.
Yeah. I'll write it again. So A union B. Okay. It will be a union of 3 groups. So a sort of pink thing is green plus yellow plus blue. Or union of green, yellow and blue. So this is A minus B. The difference between B and A. Then it's A intersection B, and it's B minus A. Again, this might be a useful thing. Well, let's look at the only problem with Venn diagrams is you have to draw them again and again and again. So again, let's look at, this time, let's look at the case where I have 3 sets. So let this be set A, this set B, this set C. Well, let's identify here what A union B intersection C. Where is that? That's A union B. A union B is everything that's in A and in B. Or in B, sorry. Okay, so that's this part. Now everything that's in C, it's this. Yeah. So whatever is shaded is this element. Okay, so it's A union B intersection C. Now we know from the rules that this is the same as A intersection C union B intersection C. I didn't prove that, but you can prove this from 2 of the rules. The commutative rule and the whatever associative rule. Okay, let's look at that. So this is A intersection C. A intersection C is everything that's here. And then it's B intersection C. That's everything that's here. And a union of that, yes, there will be a few things that are joined, but that doesn't matter for the union. So the union is indeed what we need. Okay. So it's an illustration of something we could have proven without the Venn diagram. And I said it in my words, but what you would do is you would first use the commutativeness. So you write A union B intersection C is C intersection A union B. Yeah. So I swapped because it's commutative. And then I use, I'll just go back, algebra of sets, so commutative. I use this rule to put C in front. And then I use the associative rule. So I use, actually I didn't, I was just going this way, but, yeah. Sorry, no, it's this one, it's this one. So I'm using A, which now is my C, intersection, union of what is now BA and B. And now I can use this. So I'm using the distributive one, not associative one. So, and then plus, and this is distributive one, and that gives me C and A, or C and B. And then I use the commutative rule again, and then I get A intersection C union B intersection C. Okay, so I can use Venn diagrams to illustrate, and I can also use algebra of sets to actually prove things. Right, let's look at more examples. So, right, well, let's just look at a couple more examples. So if I have A, B, again, A, B, let's mark here A union not B. Well, what is not B? Not B is everything that's not in B. Then A is this. So therefore, A union not B is everything that is either in not B, which is the yellow bit, or is in A, and therefore it's everything outside. That's a nice color. Beautiful. And including that as well. Oh, wow. Bingo. Anyway, you see what that is, okay? It's just this bit, but without the bit that's common here. Okay. So again, I can probably explain what that is. It will be, so it's everything but not B. So it's essentially omega minus B. So it's B. No, it will be the same thing. Anyway. Okay. I don't think you can sort of simplify it. I could make it more complicated. Okay. But this is just an illustration of what you can do with Venn diagrams. So, beautiful colors, if you want this. Let's look at something. Let's look at A, union B, but let a complement of this. Those of you who know logic or know set theory, they probably recognize where I'm heading. So if this is my omega, I've got A and I've got B. Yeah. Then where is A union B? Where A union B is all of that. Yeah. What is therefore the complement of that? Well, the complement of this is everything that's outside.
Omega minus A union B.
Sorry?
Omega minus A union B.
It's everything, so it's omega minus A union B. Sure. Yeah. But then let's think for a moment how we could build that? Well, let's look at not A. So again, I've got my A and B. Let's look at not A. So not A is everything here. Let's look at, I'll just make it slightly smaller. Let's look at not B. Well, not B is that. How can I get a yellow thing out of this too? Well, what I need to I need to exclude from omega everything that's either in A or in B. Now the problem is this one excludes everything that's not in A. This one excludes everything that's not in B. And I need to exclude not only, like if I'm looking at this purple thing, I need to exclude this part of the purple thing. This is okay. So this part here is okay, everything else is okay. But this part is something I don't want. But this part is not in that picture. So this is white, this is white. That will be white, that's okay. But this, I want to get rid of this part. So if I take an intersection of the purple and the green, what I will get is the yellow. Do you see that? If I take an intersection, if I say it's everything that's not in A, so it's the purple bit, and then I want to exclude this part. So if I take what is in the purple thing and in the green thing, will give me a yellow. So we can just look at it. Okay, everything here is okay, everything here is okay, everything here is okay. I don't go here, that's white. And then I want to go here, but that precludes me, because that's white on that map. So therefore, if I take an intersection of the green and the purple, I get what's yellow. And that means that this is the same. This is the same.
Union or intersection?
Sorry? Sorry, say it again.
It's the union of lila and green that will give where you are in intersection.
No, it is an intersection. It's not union. If you took union of purple and green, you would get omega.
Not omega,
Not omega, omega except the thing in the middle. But you get too many things. I want you to think about this, and basically you just follow this. So if I take, so this is okay. All of this is okay. All of this which is outside A and B is okay. Now I don't want to get into this region because this finger will tell me no, no. And I don't want to go into this part here because this finger will tell no, no. So therefore, it must be an intersection of the two. I need to preclude from things getting into A and B. You just think about that, write it down, sort of think about how to get those two things combined here. It's probably actually, I'm just thinking, okay, I'll try again. I'll try to go from here to here. Okay, so reverse this. Because I think I see a lot of unconvinced people. So let's just have a look at that. So, the not A, this is not A. What about not B? not B, is this. So what is therefore not A, intersection not B? Well, it's everything that's colored in both. It's everything that's colored both yellow and blue, and that's green. Okay, in this mixture of colors. Do you see that? So everything that's both here and here will be colored in green. Okay, let's color it in green on a separate picture. Okay, everything here, everything here, everything here, everything here, everything here. Yeah? You agree with me? But this is the same as A union B complement. Because whatever is in white, it's A union B. Was that easier? Okay. No.
Which term would you pick?
Which, sorry?
Which one would you pick if you were going to describe that graphic?
Which one, this or that? So,
Would you say it's not A union B, or would you say it's...
either. They're equal. They're the same.
Okay.
So in a sense, it depends on how you're building the case. If you say, so it's either, so what I'm looking at is not A union B, is the same as not A intersection not B. So you can go either this way. So I could say, suppose that A is a nice weather today. Suppose B is a nice weather tomorrow. So I can either make a statement, the weather is not nice today and the weather is not nice tomorrow. Or I can make a statement that the weather is not nice today or tomorrow. And that's actually the first of the so-called De Morgan's laws. I have a sort of picture in my mind of De Morgan with sort of lots of hair, which means that probably like 17th or 18th century guy. But with the first two letters suggest that perhaps he was French, but I don't know. I haven't looked up, sorry. I didn't come prepared for this. So, but this is a sort of sounds like this would be a sort of 17th, 18th century work where people started to formalize different rules of logic. There's another De Morgan law, which is A, if I negate an intersection, I get a union of negations. So let's have a look at this. Let's try to use, this is a bold thing to do. Let's try to use the Venn diagrams again. So if I have my set A and a set B, then the intersection of those is this. And that means that the complement of the intersection is everything except the blue thing in the middle. Let's look at A, union, so complement of A, union complement of B. Again, A, B. So a complement of A is everything that's not in A. Everything that's not in B is here. Okay. And the union of that will be everything that's colored. Okay. It doesn't matter which color. It could be yellow, or it could be blue, or it could be both. Everything that's colored is in that set. And that means it's everything, so it's everything outside this white thing in the middle, which is exactly what we have here. That was easier than the previous one. So that's the Morgan law. In a logic sense, it says it turns an OR into the A. So this is what I said in the weather example. If I negate the fact that the weather is nice today or tomorrow, it means that the weather must be not nice today and not nice tomorrow. If I negate the fact that the weather is nice both today and tomorrow, it means that the weather is either not nice today or not nice tomorrow. In a language, in a sort of normal language, we use these terms and or a bit more vague. Okay? This is more strict way of treating the or and state. Okay? So this is the Morgan's laws. Let's look, go back to, so as I said, a lot of things can be illustrated or proven by using Venn diagrams. A lot of things can be proven without using, or actually should be proven without the use of the Venn diagrams. Jordan and Smith has a number of examples of those. Let's just have a look at, well, let's have a look at A intersection B union A intersection B complement. What's that? Let's not go into Venn diagrams. Let's just try to use the laws of the algebra, of set algebra, to do this. So this is, again, we'll be using the commutative case. So we can write this as I think what's the best way of doing this? Right, we can just reverse. Remember that A union B union A intersection B union A intersection C is A intersection B union C. Remember that? We're doing this the other way, but this is one of the rules. Sorry, this bracket shouldn't be here. So this is A and then intersection B union C. So I can use this to write this is really an intersection B union not B. B union not B is omega, so that's A intersection omega, which is A. Let's do another one. A union B union A minus B. What's that? This is slightly more complicated. Sorry? Yes? We can. I said I don't want to use Venn diagram here. Okay? I said you could use Venn diagram, But you would be using Venn diagram to illustrate, not prove. This is a proof. So you're just using the laws of algebra. I mean, I do accept proof by Venn diagram as well. So you could have used proof here as well. Okay, so let's think what that is, how we can work with that. What is A minus B? Well, this is A and not B. So it's an intersection of A and not B. So this is A union B, union A, intersection not B. So we can now group things. We can say this is A union B union A and B union not B. Okay, that's using the fact that we've got a B here and we've got the B union, so I can move this bracket to this bracket here. Maybe I should have done this first. So essentially what I do is I move this bracket. Instead of having A union B union something, I use A union and then have B union A intersection not B. Okay. So I can do this because it's I can move things, I can move brackets. And then I can, again using this, the rule up there, the dissociative rule, I can split that in that way. This is the same as A union B union A intersection omega. Because omega B union not B is omega. Now anything intersection omega is the same thing. So this is A union B union A. And this is the same commutative A union B. So now I can move the brackets. A union A, B union B, which is A union B. Okay. And that's simplification. That's how far we could go with this simplified discussion. Again, why are we doing that? You might start wondering. And the reason is that what we will do is we will be asking questions like, what's the probability that there is a nice weather today and tomorrow? Or what's the probability that there is a nice weather today but not nice tomorrow? We will turn this into a statement like this. So suppose that A is a nice weather today and B is a rain tomorrow. Okay? Then the question, what's the probability of having 2 nice days in a row will be a probability of A and not B. So I want 2 nice days. I want to, did I say nice? I meant sunny. Because the weather is nice always. It's the size of the umbrella. So, what's the probability to have 2 sunny days? It's the probability of A and not B. And that will allow us to ask more and more complex questions and turn it into unions or intersections of events. Okay, exactly. So things like, I could ask what's the probability. Well, for example, let's say that C is not B in my case. So C is the probability of a sunny day tomorrow. Then what's the probability of 2 rainy days? Okay, both are rainy, yes?
Why not define the probability of 2 days not being probability of A union not A, but in terms of E?
No, because this is today, this is tomorrow, and they might be different. This is today, this is tomorrow. The probability of a sunny day today might not be the same as the probability of a sunny day tomorrow.
I'm thinking of making it not A rather than
So B being not A?
like probability of A intersection and probability of not A.
Well, it depends what you want to say. C is a probability of sunshine tomorrow, which could be different to the probability of a sunshine today. In which case you can't just negate them. You can't swap them. Anyway, we'll get to that. What I'm just showing is we will be making statements that will then turn into the sets and associate the probabilities to those. So for example, I'll just finish that. So for example, the probability of 2 rainy days will be probability of not having sun tomorrow, sun today, sun today and not sun tomorrow. Okay. And then we can sort of turn things into this. Yes.
So the example before this.
Sorry?
The example before this.
Yes.
Is the reverse true? Can you just tell me? The example before this.
Yes.
Is the reverse also true? You know, we're able to prove that not A should not be equal to A and B. Is the reverse true?
So like.
But before this, can you do that? Yes. Yes. Can we prove that A and B is also is A minus B?
If I reverse things here, I would need to think about this, but probably yes. So I mean, if you had, I'm not sure I follow. So if you had B union A union B minus A,
which is equal to A and B.
You would need to check that. I suspect yes, but yes, but it should be because you can just rename A and B. Okay, so this is just the motive. Sorry.
So the last one can be not A union B.
Yeah, this is just, what do you mean by 2 rainy days?
Yeah.
So 2 rainy days should be rain today and rain tomorrow. I was just actually thinking about that, so thank you for being vigilant. That should be or. Okay. So rain today and rain tomorrow is the same as ask the end. You just anyway. I leave it to you as an exercise. How are we doing with time? We've got probably about 10 minutes. I'll just go. I'm going a bit slower than I anticipated. No, I'll leave it as an exercise, so don't be too. We will have some examples from that. There are. You can read about the more examples in Jordan and Smith. There are some examples there how you can use things to count as well. So an example that Jordan and Smith says is that if I have a product and a product goes through 3 quality stages, and it can fail at each probability if at these stages. We're not talking about probability. Pi is a set of those that passed set 1, set 2, set 3. So I is 1, 2, 3. So essentially what we have, if this is the set of all products, we have products that passed the first stage, products that passed the second stage, and the products that passed the third stage. We assume here that those that go through stage 1 are not past stage 1 are not thrown away. Because otherwise it would be a different situation. And then we're told different facts about those. So for example, we're told that there is 1,000 elements in it. And then there is a whole list of things. So 8 fail all. And that means fail all means they're outside any of those. So there are 8 elements outside. Then it says that 20 pass P1 only. So 20 elements are in P1. 31 are in P2. 17 are in P3. The question is, how many elements are in the middle here? It's slightly misleading graph, because actually this element here is much bigger. And you can see, because the sum of those 20, 31, and 17, yeah, so it's a slightly misleading. So 20 is just 20. I should have said 20 pass P1 only. So that's 20. That's 31.
Only means that it doesn't pass.
It doesn't pass the other ones.
So it's not.
Oh, I'm sorry. Of course. Passes P1. Oh. P1, P2, P3, and you're absolutely right. That's passes P1 only. That's 20. Then passes P2 only. That's 31. And then passes P3 only. That's 17. Okay. Only, P1 only. So the question then is, and then we need to know something. Well, we can't, because we have no idea what's in here. Okay. So that's where we need some additional information. So in addition, it tells us that 814 pass P1 and P2. So P1 and P2 altogether is 814. Then P2 and P3 is 902. So P2 and P3, this is 902. And then 800 pass P3 and P... Sorry, there is P1 and P3. Okay. But you can see that actually we're triple counting a number of those.
Yes.
There's a whole group here that's counted within those. And that's what we want to find out. So we want to find how many there are in this region. So what we can do is we call that K. And then we just identify what's in here. And that's 800 minus K. In this region is 814 minus K. In this region is 902 minus K. And then the sum of all of those altogether must be 992. So what we can then get is that 992 equals 20 plus 31 plus 17 plus 814 minus K plus 800 minus K plus 902 minus K plus K. Okay. And just a calculation, this is 2584 minus 2K, and therefore K must be 796. Okay. I think that's a good. There are a few other things in Jordan and Smith that you can look at. There are some other examples there, and we'll do some more examples in the tutorials after the break. The last thing I want to mention is, well, I've just signaled that. You can read about this more in Jordan and Smith, but I'll come back to this. Is the number of elements in a set, because we will need this to actually move into probability. But that will come after the break. So have a good reading week. Enjoy the time. Do read, not only have a break. And as I said, I will